Happy Monday, everyone. We are going to get a chance to finish up acids and bases today. Take a little quiz on that tomorrow, which will be open notes and just so we can, put some closure on our acid-base unit and then move bravely into the very last unit of AP Chemistry. Okay, so this actually covers 4 concepts, but there's actually a ton of overlap with some of the other stuff. Oh, yes, I did get a haircut. Look at that. Whew, short spring haircut. Happy haircut for the C-Rex. Looks even more like a dinosaur now. What we're going to do is talk about this buffer concept. You might not be aware of it, but there's a brand of aspirin and painkiller called Bufferin. And what it does is it has a buffer in it so that when you take the acetylsalicylic acid and put it in your stomach, sometimes that would upset people's stomach if you have sort of a delicate stomach. So the buffer will prevent the pH from changing. And that's really what they do, is they resist changes in pH by just doing a chemical reaction, kind of sopping up the extra hydrogens or sopping up the extra OH ions so that you can add an acid to it, you can add a base to it, and it resists changes in pH. Okay? And then we're going to talk about how this applies to indicators. And again, that's going to be overlap because we did that nice lab where we talked a little bit about that, but I kind of provided the indicator for you. But it's really easy to figure out which indicator to use. A lot of the concepts in this chapter are review, as we mentioned, the common ion effect we've talked about before. So if you have this top system right here at equilibrium, you got this really weak acid, so it's going to kind of hang out on this side anyway. And then now you throw in potassium fluoride, which is a soluble salt, and the common ion is this one. If you add to this side, shift to the left. There's a nice beautiful arrow right there. Add to this side, shift to the left. And that is according to Le Chapelier. Likewise, if you had this system, and this would cause back here this would change the pH, right? Because you're going to have less H3O plus, less acid, so the pH would actually go up by adding a salt to the already existing system. And right here, if you did this, the common ion is ammonium, so you add there, shift to the left, making less OH minus. So it's a way of kind of cleaning up and getting rid of that OH. So the common ion will cause the pH to drop, in this case, become more acidic because you're removing OH from the system. As I mentioned in the intro, buffers resist changes in pH. And here's how you make one. It's a weak acid and its salt, or a conjugate base. A weak base and its salt, which would make extra conjugate acid. All right, so let's see some examples of that. It's a little easier to understand with an example. So you have acetic acid, which is a weak acid, and it breaks up into H plus and acetate. And then you add this sodium acetate. So the sodium is just going to be a spectator in this case. And then you'll end up with lots of conjugate base. So this is what makes such a good buffer. Okay? So you've got lots of weak acid and lots of conjugate base, because you have added more of this, which you wouldn't have hardly any of it if you just let this top one go to equilibrium, because this is a weak acid. And remember, I don't want to give up my hydrogen. So here they are already having given up their hydrogens. And remember, that would be a relatively strong conjugate base. So that's going to be able to react with either one. So if you think about it, you've got ways to get rid of both hydrogen ions and OH ions. Now, the capacity of a buffer, I'm going to explain that a little bit more. So if you have all of this and there's an extra hydrogen ion, it's going to scarf it up because you have that extra conjugate base. If this comes into contact with a strong acid, a strong base, the base will rip off that hydrogen and make this, which isn't going to change the system that much because you're making this. And when this one picks up the extra hydrogen, and you got more of that, and it's just a really nifty little balance between those things. Okay, so this slide, circle this one because that really does a good job of explaining the process of how a buffer actually works. All right, now buffer capacity, you can just think of as the strength of a buffer. The bottom line is you want higher concentrations, more to sop up those extra hydrogens and to react with the added OH ions. Okay, so the more you have of these things, the stronger the buffer tends to be, and that's going to come up in one of our problems here. So we go back to our good friend, the Henderson-Hasselbalch equation, remembering that on the bottom is the weak acid, and then this is its conjugate base, or the concentration of the salt with these buffers. Okay, so you can see a relationship with, again, review of things that we've already done. Okay, now many times buffers, the concentrations of these are very close. All right, and you can see when that happens, that will be the log of 1, which is 0, and then it's going to be pH equals pKa. This is helpful when choosing the pair. If you want it to be at a certain pH, you would choose a weak acid with the pKa value that is very close to the pH that you want it to change at. And we're going to do those problems in reverse too. All right? So, when you take a very weak acid and there's salt, the buffers tend to be at a higher pH because it's such a weak acid, and then the basic anion actually would increase the OH concentration a little bit right there. And if you had a little stronger weak acid, all right, so we know that there's only certain ones that are strong acids. So, but of the weak acids, some of them are stronger. Those would have a tendency to add and increase the hydrogen ion concentration, which would make the buffer at a lower pH there. So these are actually two real common buffers. We have little capsules that we use in the lab. You just dump them in to deionized water, and you got yourself a buffer because they have already calculated the weak acid and conjugate base and vice versa. So this ratio right here, it gets a little bit tricky. Okay, when we're figuring these problems out, we're going to do a couple of them just to kind of help clear that up a little bit, and then you can look at the examples tonight for homework, as I will be posting all the answers for the problems, and you can do as many as you want or as few as you want. So adding small amounts of acid or base would cause a very small change in the pH. Okay, that's the idea of what's happening here. Okay, because the log of it tends to be very, very small numbers. Okay, so let's go ahead and do some crunching here with some of the numbers. So here you have a buffer solution where you take this many grams of salt. I kind of like how they wrote this. Normally you'd write NaC3COO, but this is really the business part of it. Na is just tagging along. So and then it shows you the similarity with the acid right here. So you do have a known concentration of your weak acid. We don't know what the concentration of this salt is yet, but we can easily do that. Now we're going to find the pH of the buffer solution at a given temperature. Okay, so Ka is given for that given temperature. To find the concentration of the acetate ion, very simple. You just take the 85 grams, you get your purple sheet out, and you look up the molar mass, and you're good to go. All right, and it turns out it's 1.06 moles of the sodium acetate. Okay, now that's in 1 liter of solution. So to figure out the concentration, it's just moles divided by liters, 1.06 molar acetate. And this is where we say the sodium doesn't make any difference. Okay, you need to include it in this first part to get the correct number of moles. But right now we know that this is in a 1-to-1 molar ratio, so you got 1.06 molar acetate. Okay, so to find the pH, you're going to use Henderson-Hasselbalch. We just did these. This 1.8 is provided for you. And we figured out that concentration, and this one you get right up there. It's 1 molar of the weak acid. So the salt a little bit stronger. So this is actually going to bring that value up a little bit. Now this is really important that you type this one into your calculator. Okay, figure out the order of operations. I did it just to make sure that there was no variation at all. But this is the correct answer, and that is your pH. That's one of those where you'd hate to do all this work and get everything set up perfectly and not come up with the right answer. So make sure you crunch that one, and I will see you on video number 2.